These are in listen-only mode.
Okay, hello, my name is Adrian Jensen with Predictive Engineering, and today we're going to be talking about the Femap 11 release. New release, version 11. There's some new updates here, and there's lots of different updates to the new version of the software. We're going to cover a few of them in depth, or more in depth, and then we're going to dive even deeper into some of the ones like 3D composites later on. But if you've done any of these webinars before, you've heard me. Again, my name's Adrian Jensen, and then we also have Nathan Anderson on the line.
Hello, welcome everybody.
If you haven't done one of these webinars before, you can ask questions or use the little chat with the GoToWebinar dashboard. So if you guys have questions, or if the audio goes out, or you can't see the model at any time during the webinar, be sure to pop something into the questions. And while I'm working through the webinar and you guys have questions, you can punch those in and Nate can help address those as we go. All right, and we already have a question. Who is Nathan? So Nathan is another one of the engineers here at Predictive. So George Laird is our principal, and then Nathan and I, we're the staff engineers. We do consulting work as well as technical support for Femap and Nastran. All right, we still have some people rolling into the webinar, but it's 8:30, so we'll get started, and I'll do a quick overview. So this here, let me move stuff around, is our list of new features for version 11. One of the big ones is the ability to attach to external results files. So before version 11, you would just import results into your model file, and all of those results would be saved internally. With this new attach method, there's several benefits as far as load time, save time, model file size, and we're going to do an example of that one, and I can show you the speed and the model size benefits there. There's some improved graphics performance. There's the ability to create geometry from mesh, and this is a nice one if you ever get a model from somebody else or some sort of legacy model, and there's no geometry in the model, but you need to update the mesh, you need to remesh something. There's always the option to move nodes by hand and split elements, and it can be rather tedious. With version 11, you can use the nodes and elements to create new geometry and then remesh that new geometry you've created. So that can be very handy. Super element support. This isn't really a commonly used thing by most people, but you can now use super elements within Femap and Nastran. Previously, you could export super elements, but there's new support for internally creating these. Streamlined XY plotting. If you've ever done any sort of data plotting with your Femap model data, you know how it's a little bit funky. It's not the easiest thing to use. Personally, I would usually just take my data to Excel and do all my plotting there, but they've really overhauled this XY plotting. It looks a lot better, it's a lot easier to use, and we'll walk through an example of that. There's some more integration for Nastran within Femap, and the one we really want to focus in on is the solid composite element. So you can now model laminates with 3D hex mesh brick elements. We'll be doing a quick example of this, but we want to work on a white paper for this because it's a very complex topic and it's going to take some work. So I'll do a brief overview, and then in the future, you can look forward to a white paper from Predictive Engineering as we really dive into this one. And lastly, I'll do a little nice trick they've added to Femap, which is mesh splitting, which is good for really any element type besides tet mesh. Let's get started with the attaching results. This window you see here is the results attach management, and currently, Femap is supporting Nastran output, OP2 or FNO for NEI Nastran. And as new releases come out, they'll support more analysis types, Abacus, and ANSYS, etc. And this little graphic here kind of shows what's going on. This is the Femap database. This top green chunk here is your model. That's your elements, your loads, and your results are this big lime green chunk over here. And this is kind of representative of the memory size. And with internal results, you've got a little bit of overhead for processing the type of results that Femap generates, like your von Mises stress or your enveloping stresses. And as you internalize those results, your model files get large quickly. And so what we're going to do with this new V11 is, rather than internalizing results, we're going to attach to results, and it keeps our model file nice and small. Here's kind of a quick preview. I've done some testing on one of my models, and here's the actual file folder of the model. So the model is about 250 megabytes, and for this example, I had about 4.5 gigabytes of data. And I did it with version 10.3.1. I imported my results and saved the file. And so to save the file, it was about 30 seconds. To open the file, it was about closer to a minute. And I did the same exact model with version 11 using attach to results. And I was getting about 2 seconds and 4 seconds for the save time and the load time, respectively. It actually took longer for the graphics to update than it did for me to load or save the model. So let's do a quick run through of that. I'm going to open version 11. And here's our XY plotting, but we'll get to that soon. And I'm going to open this version 11 model, no results. So this is a kind of a complex satellite structure we did some vibration work on several years back. And the model is, you can see in the bottom left corner, about 800,000 nodes. So it's getting up there in size, but the fact is we needed multiple output sets worth of data, and as we got more and more output sets is where things got really complicated and slow. So let's go to File, Attach to Results. Previously, if the results weren't already internalized, you would do Import, Analysis Results, but we're going to use Attach. And you have this little manager here, which makes things nice and organized. We're going to do Attach File, and here is the OP2 files. So this is what Nastran generates when you analyze the model. And generally we have our clients set up your Scratch directory, and all of your output files get dumped into your Scratch directory. So that's where you'll find these. I'm going to grab all of these, and if you look at the size, they're all about a half a gig. This is a monster here. It might have multiple output vectors that we've created or added. That's 4.5 gigs. So overall, we've got about 7 gigs of data here. 1, 2, 3, 7.5 gigs. And I'm going to grab all of these and open these up. And you can see the little progress bar as it just whips through them. So these are all now attached. I click Done, and I can expand the results section of my model info tree, and there are my results. So like I said, I double-click on that one to activate it. It's probably going to take longer to render the graphics than it is to import the data or attach the data. So I've got all of these results now available for post-processing within Femap. And let's go ahead. We're going to File, Save As, and let's call this version 11 with results. I click Save. There's my progress bar down there. In just a few seconds, and it's done. So I can close this. And just to show you guys the speed, I'll open this model back up. With results, you see the model size is only about 300 megabytes. So we've only added about 40 megabytes of size to the model file, even though we have a massive amount of results. Open that up. And there we go. About five seconds or so. Now let's say we want to dump some of these results or get rid of them. We can always go back to the attachment manager. There's a couple of different options here. There's unload or there's detach. I'm going to select one of these and unload. And you can see my green check mark goes to a yellow check mark. I click done, and those results are no longer available to me in the results section of the model info tree. They're still kind of hanging out here in this manager. And what unload does is it removes them. It doesn't perform the attachment, but it still remembers the directory for those. So if I close this model, open it back up, these will still be lingering here in the manager, but Femap won't go through the process of actually attaching the results. If I want to remove them entirely from the list here, I click detach, and they're gone. When I save the model, reopen it, you'll see the list like it is here. Say you want to internalize some of the results. You want to share some results with a friend, a coworker. You're going to send them the model, and you want the results included so you don't have to send them the model file and the OP2 file. What we can do here is save to model. So this is going to internalize the results similar to how it worked previous to version 11. So save to model, and here's my output set. And now I have some options. I don't have to internalize everything in the result set. You can see I've got all these output vectors, displacements, beam forces, plate stresses, solid stresses. So I'm just going to limit my data to total translation. If we're working with some vibration work, I just want to show somebody the different mode shapes. I'll just do translation. Okay. If I wanted to limit my data even more to just a select node group in the model or an element group in the model, I could create those groups and choose those groups here for even more limited output. I'm going to click None, which means it's going to import that data for the full model. And there we go. If you look in the results section of the model info tree, the old icon is back. So these results are now saved in the model file database. You can click Done, and if we save this, you can see the save time slows down just slightly because we now have internal results. If we go to this output set that we've internalized, we lose the contour because there is no stress contours. We just have translation. I'm going to right-click and go to Post Data. Take a closer look at our results, and that's all you get: the translation output vectors. So this is it's a really useful tool for a lot of different reasons. You can limit the data you have in your model. You can speed up the loading and saving of model files, and you can reduce your model file size. Now the output size is going to remain the same, but it's a separate file. That's the OP2 file. One last thing I want to cover with this before we move on, let's go back to the manager, is memory mapped file. And what this option does is if you have a ton of RAM, it will open the results entirely in RAM, and that speeds up the process even more. So as long as your OP2 file, or as long as you have enough free RAM to fully grab the OP2 file, you can use this memory mapping to speed things up even more. This, if you guys want more information on this, go ahead and check out the new help. Grab that, and they've updated the Femap help. There's a new format as well. It's not using a browser. They've got documentation on attaching to results files.
Hey Adrian, it looks like we have a couple questions. Brian is asking, you see that there, so when you plot, you're associating with a specific output with a specific graph, or are you loading in your results in random order where you mess up all your graphs? Do we know the answer to that yet?
Let's see here. Can results be binary? Well, are you talking about the graphs? Okay, I see. Specified graph. I think this might be addressed a little bit when we go into the plotting section of this, because now the graphing within Femap is also updated, and so the way that you select data for your XY plotting, it's going to be different. It's going to link directly to these output cases. So as long as you don't detach and retach everything in separate orders, I think your XY plotting, your graphing, is going to remain consistent with the output sets you've selected. Another thing about the graphing is that you manage it in 2 separate steps now, and so it's going to be easier to know which data set you're using in your graphs. Let's see what else we have here. We might grab a few more of these at the end just so we can get through all the different topics here. Support for COMSOL. Right now we're only supporting Nastran OP2 and FNO, which is the NEI Nastran output. But the development team does plan on expanding this for supporting other outputs. Okay. I'll save these questions, and if we have time, we'll come back to them. If not, I'll be sure to address them by email after the webinar. Okay, so we're going to close this one. Let me save this. The next thing we want to get into is our XY plotting. So I bring back this here. So our XY plotting, there's new graphics. There is an unlimited number of curves. I think previously you could only get up to maybe 8 curves with your plot. And plots can now be saved to the database like a free body diagram. So if you had worked with Femap prior to the free body diagram update, you know you get one and it was hard to set up and that was all you got. The new version, you can set up multiple, you save them, you can switch through them. And the plotting is the same way. You're going to have a database of data selections, and a database of plots. And you can mix and match these two, and they'll be saved with the model file. So we're going to do an example of that. I've got a little simple tower here. And this thing is loaded up to buckle. We ran a nonlinear analysis, so we've got a bunch of different output sets. And this thing loads up and up and up until a point where it buckles. And what we want to do is maybe plot the deflection of a couple of different nodes versus the load value. So I'm going to open up charting, which is the pane for XY plotting. And this is a pane just like model info or entity info. You can move it around. You can, if you have a second monitor, you can move it off to the side there. And there's a couple of different things to work with. The far left button is the chart manager. And we select this, and this is where we choose a lot of our graphics for the chart. We're going to create a new chart, and we'll give this will be chart number 1. We can choose the style. We're just going to do a line, and we're going to select our data series. Right now, I don't have any data series. I haven't set this up. So I'm going to set up my chart, get the settings right. Then we could set up our data series. And then if we want to come back to modify any of the appearance of the chart, we can do that here. Okay. Oops. Chart 1. There we go. So we have a chart. Now I'm going to go to the data series manager so I actually have some information to put into my chart. We'll do a new data series. We're going to call this displacement versus load. For our type, these are the types of XY plotting that you used to see within View Select. Now they're all just different chart types. And if we work our way through this, we have XY versus ID. So that would plot the deformation value of a node versus its node ID number. Not the most useful in this case. There's XY versus set. So we have, I think, 17 output sets. Or there's XY versus set value. And this is the one that we want to use because we want to use the set value. The output set title gives our load value for the nonlinear analysis. So we can plot our deformation versus our load. So here's our output vector. We've chosen to use all of our sets here. And now we need to pick a location. The old version, you would have to know your node ID number before you started this process. You'd have to find it, write it down. Now, if you put your cursor in here, you see out in the model window, it snaps to nodes. Or if we want to select multiple nodes, we can. So we could get one here at the top of the tower, maybe part way. We could grab nodes at the cross sections of these stiffening members. There we go. There's 4 separate nodes. And then the nice thing about this, we've selected 4 nodes. We have 4 data series. So we don't have to create individual data series for each of those. If we select multiple nodes, it'll use those same settings and create a data series for each of these. So we're starting to get our little XY plot built up here. If we go back to our chart manager, we can edit this chart. And here's where we get to play around with some more options. Use output set from data series. Here we can manage our data series. If we only want to display a few, apply, there they are. And then the rest of it is graphical options. Do we want a log scale? Fonts, we can give titles to our chart here. Displacement versus load. Chart title, there we go. And you get to play around with font sizes. You don't have to have the same font size for everything. You want to bump this up a little bit. So it's beginning to move much closer to the capabilities of Excel's plotting, but you get to do it within Femap. And it's very quick and easy to modify your data series and update your charts with these data series. So right now we have 4 data series. We only have 1 chart. If we want more charts, we can do that. Let's select, say, the first chart has 1 and 2. The second chart could have 3 and 4. Okay, done. And there's our second chart. And we can easily switch between our 2 charts. A lot of this, this is going to be just kind of hunting around within the chart options here, playing with sizes, playing with colors. That's all personal preference. But it's all nicely located right here in this manager. It's also very nice, copy to clipboard if you want to put this in an engineering report. Oops. We now have some nice graphics to drop in. So nice new feature. Again, these charts get saved with the model file, so if you close this window, you haven't lost all of your charts. They're still going to be saved there within the manager. Okay, so we have some more question. Graphs are associated with cases. I like to plot transient results as one line for each time step. So this one here is multiple time steps. We're plotting the displacement through these time steps. I'm not sure if that answers your question. And I might have to do offline, I'll do a test as far as attaching the results. We'll create some graphs, remove these, reattach them, and see how it affects our data series. Because that's a good question. Once you create these data series, are these linked directly to these output sets, and these ID numbers? It's a good little test to run. Okay. Moving forward. Okay, 3D composites. Like I said, this is going to be kind of a brief overview because it's a rather complex topic. But previously, you could only use 2D plate-style elements for laminates. And now you can, it's supported with 3D hex elements. And there's several advantages to this. There's more accurate interlaminar or delamination failure. You can get more accurate stresses at a change between layup. Maybe you're going from a 8-ply to a 7-ply, and at those interfaces you're going to get a little more resolution in your stresses. And you can also model some more complex structures. Again, this only works with brick elements, hexes or pentas, 1 to n plies per element. The ply thickness is relative, so we're going to use this example model here. And regardless of what thickness I give to each ply when I set up my layup, it's all going to be relative, and my total stack is going to be use the model thickness there. So we're giving relative values. As far as failure theories, we've got the ply failure theories that were available for the 2D laminate elements, but we've also got normal failure. So the separation of laminates normal to the stack. I'm going to bring this up. We've got a new model. So this model here is currently just modeled with plate elements. That was a good starting point. We don't have to go through the meshing process. And I've got loads and constraints. So all I'm really going to need to do for this is create my material, my layup, my properties, and then we can orient our properties. So we'll start with the material. It's not an isotropic material. What we need to use is a 3D orthotropic material. And I had created one and it's disappeared. But the important thing about this is, for this example at least, is setting up our elastic modulus. And for this one, I was going to use a glass epoxy. It's kind of a classic example from a composite book by Jones. And if you look under the 2D library, it's also having issues. I think I may have lost some of my materials database information here, but for a new install of Femap, you'll have a default 2D orthotropic material, which is a glass epoxy. So let's go back to 3D, and we can build our own. So we've got 3 directions, and the way I like to set this up is direction 1 is going to be aligned with my fibers. So let's give this a large value. We'll say, I believe, 780,000. I can check my book right here. Okay. And our other two directions here are going to be, let's say we'll do 26. I need one more zero there. So we've got 7.8 million, 2.6 million, and 2.6 million PSI. So what this represents is direction 1 is aligned with the glass fibers, and that's going to be the stiffest direction. Direction 2, we're just pulling up against the epoxy matrix, and it's going to be much less stiff, about 1/3 of the stiffness of the glass. And our third direction is going to be the same. So what we're really seeing here is just one direction for the glass fibers. We can give a Poisson's ratio for all of these. And we're going to need, we'll leave the rest of this blank. This will give us a good idea of how we're going to orient everything. As you get more comfortable with these, we can start to put in our stress limits. And I'll try and attach an example material model. Like I said, I had a sample material built, and when we upload this to the web, I'll be sure to include that sample material model. I've broken this up into 3 different properties because if we imagine this as a composite part, maybe we're going to start out flat and we want to align our fibers in the global Y direction. Once it's bent, we think our stack direction is going to be different for each of these 3 tabs. This main body here is going to stack up in the global Z. These red tabs on the end are going to be stacking up in the X direction, and these orange tabs on the side, they're going to be stacking up in the Y. And I'm going to need, that's important because I'm going to need to set up my material angles for all of these. So let's create a layup. Let's just do a 4-ply layup. And we're going to select our material that we created. We can do a thickness and an angle. Previously I mentioned that our thicknesses are just relative, so I can set each thickness layer to 1. If I do 4, it'll work out that each ply is 1/4 of my total thickness here. A new ply. Maybe I'm going to rotate each ply 90 degrees. And there we go. So we have a 4-ply. Each layer of the ply is rotating, and we can get a little preview. Now this is just the same as modeling 2D composites at this point. Besides the fact we're using a different material, this is the same way you'd set up a 2D. Okay, we have a layup. We can now create our properties. These are just solid properties, and we're going to need to switch from a solid element type to a solid laminate element type. You can see that there. This is a new option. We can choose our layup that we created, and let's give this a title. We can call this End Tab, and this sits in the ZY plane. The tricky part here is selecting our ply stack direction. If you worked with 2D laminated elements, you would simply go to Modify, Update Element, Material Angle, and you could pick your material angle to align your fibers to. Now we choose Apply Stack Direction. And there's six different options here. So let's go ahead. I'm going to do a quick little screenshot of this so that we can draw on it a bit. Windows snip. And let's see if this works. Okay, so for this end piece here, draw this out. Is this showing up neat? Alright, so let's say that we want our ply direction or our bottom layer fiber alignment this direction. That's our global Y. And if we think about this as a 3D structure, it's got thickness in this direction. Our stack is going to be stacking up in this direction, and so that's the global X. And if we look here, ply/stack direction, so we're going to want the Y for our ply and the X for our stack. So if we go back to Femap, this is going to be a YX ply stack direction. If you do this wrong, Femap will bark at you. So you get a little bit of hints once you run the analysis. It'll let you know. It'll give you an error if there's an invalid ply stack direction set up. Okay, let's do a different color so we know we've set these up properly. So this will be End Tab. Okay, now for our side tab. and these sit in the ZX plane. Again, let's do a, I like to draw this out. So now we have these tabs here sitting in this plane. And we talked about our fiber alignment for maybe our bottom ply. We wanted it in the global Y. But as this tab is wrapped around here, our fiber direction is going to wrap around and be in the Z direction. And that way it's going to be continuous with these other sections as we set them up. We think about this as a 3D member. Our stack direction is going to be in the Y. So our ply is global Z, our stack is global Y. So we're going to need a ZY ply stack. We choose our same layup, and we want ZY. All right, last one. We can call this main body. Here's our ply, and we'll do one last round of drawing this out here. It was a bit of a painful process to get this all sorted out, and that's why I'm kind of drawing on screen, because it took us a while to run through several examples. You can imagine using the global rectangular coordinate system is the easiest. As you get into cylindrical and angled coordinate systems, things get trickier. But our main body here, oriented in the XY plane. So our ply is going to be running in the Y. And again, if this is, think of this as a 3D member, our layers are going to be stacking up in the Z. So our ply is Y, our stack is Z. YZ. Okay. Now we're going to go to Modify, Update Elements, and we're going to switch our type. And I'm just going to do this by property. So I'll take this End tab, we'll switch it to our laminate End tab. We can regenerate the window, there it is. All right, 2 more times, we'll switch our type. We're selecting our elements by our property, so everything of this property, we're going to do the side tab. And one more time, our main body here. I do main body. Okay, so everything has been updated. We already have loads and constraints. We'll just do a quick check on these ones. Y, X, okay. Side tab, Z, Y. And main body, Y, Z. All right, let's run this. And we get some errors. Let's see what we've got here. Oh, I have to get rid of my old material here. It had no material properties, and let's delete these. Come on now. Let's try that again. That old material I had 0 material properties in there. It was just a placeholder. And we still have issues. I think we might need more material properties here. I'm going to open up my finish model. As you guys can see, this isn't going exactly to plan. And this has my complete material. I've filled out everything I need here. And it looks like I need my shear modulus to finish things out. It's always good to see the demo go with a few errors, just so you know that I'm human. Okay, if we think about our shear modulus, the shear stiffness of this structure, when we think about our main body here, if we put this thing, if our fiber is aligned in the Y, our XY shear is going to be, actually let me see, it's going to be larger than our other two directions because of those glass fibers. We'll see if our shear modulus is what we need. There we go. So we have results. Now the thing about these solid laminates is if we go to contour results, we can see that we start at ply 3 up to ply 14. So that's a total of 12 plies. Even though our layup only has 4 plies, it gives us a set of results for each of our 3 properties. So what we're going to want to do, say we want to look at our first ply layer, we're going to need to choose, let's just do von Mises stress. Oops, that's deformation. So we'll do ply 3 von Mises. So that's only going to give us the first ply of one property. What about our other 2 properties? With Femap version 11, we have the ability to contour multiple output vectors. So what we could do here is ply 3 von Mises. So property 1 is going to have ply 3, 4, 5, and 6. The next property, first ply, will be ply 7. So the second property is going to have 7, 8, 9, and 10. And our third property is going to have ply 11. If you've taken my class or worked with composites, you find out that some programming is generally useful to help you manage your output with laminates. And let's contour. There we go. So we have our 3 different properties represented with our 3 contour vectors. There we go. So we're just looking at stress, but they also give you failure indices for shear, normal, individual ply failures, and all of that. Like I said, look forward to our white paper. This is an in-depth topic, and it's going to be a lot more information coming down the pipeline on this one. All right, I'm going to delete these results. This is a perfect model to show my last little trick. We're getting close, about 45 minutes here, and I want to show this. This is great if you work with hex mesh. It works with plates as well. This is mesh editing edge split. Now this isn't related just to 3D composites. This works for any sort of hex mesh modeling, plate modeling, anything. Say you just need to add a little bit more mesh density. Maybe you don't have geometry to work with to remesh, or maybe sometimes remeshing a hex mesh model like this with many solids can be complicated. So what we're going to do here is split our edge split mesh. And we just got to pick 2 nodes through the thickness here and click OK. And you can see what's happened is it's walked through our model here and split all of our elements between those nodes such that we have two elements of thickness through our full model. If you've done a fair amount of hex meshing, you'd know that to remesh this solid, we would have to resize our element size on each one of these edge curves throughout the entire thing. So this is a really handy tool. Works with plates, beams, I think pretty much everything besides tetrahedral mesh. You want to do it again, just between two nodes, and okay. All right, so a lot of information on this stuff. This webinar is going to be recorded, and we're gonna go ahead and put it online. Maybe next week we should have it up and running. But it's a good brief overview. Before we wrap things up here, there's a few last things I wanted to mention. There's our edge splitting. I wanted to mention our website, Predictive Engineering. Resources here. If you guys haven't been here and you guys need help with APIs, I mentioned that a lot of times there is some programming that will really help you out with the composite modeling. Go to our APIs. We've already written some programs that will help you envelope your results for laminates. This works great with 2D elements. We'll expand it out for these new 3D elements. A portion of our resources are restricted. If you guys have an email from me, you'll see in the signature block of the email we have our username, which is Femap NX Nastran. No password. And this will give you access to APIs. We're going to have white papers. These online seminars get loaded to our website. Tutorials. We're going through the process of updating all of our tutorials to version 11. So this is a great resource. One more resource I want to talk about is our class. We do a Femap and NX Nastran training class every 6 months or so here in Portland. Our next one will be on April 15th through the 19th. And we break it up into several sections. The first 2 days are the foundations. The next 2 days are the advanced. We get into more advanced meshing and analysis techniques. And then our last day is dedicated just to programming, customization, and automation. All the APIs that you see on our website, you're going to learn a little bit more about those during our class. That's pretty much everything. Let's do a quick roundup on the questions before we wrap things up. Nate, is there any that really pop out at you?
There's just one question about the mesh edge splitter. The question was whether you could do that through other edges, not just the thickness. And the answer to that is yes, you can split basically between any two nodes. And Adrian will show a demonstration right here. And it'll split between them. Now you have to remember that depending on what you're trying to split, it has to be hex meshable for this particular example. So if you pick two nodes and it can't develop an extruded mesh from it, it won't know exactly how to handle that.
Yeah.
But for the most part, yes, it can split between any two nodes with hex elements, plate elements, like Adrian said, just about all elements except for tet.
Yeah, when you do hex meshing and you know some of the rules of hex meshing, you know, if something will work or not, this pretty commonly follows those. You can also limit it to a region. So if we limit to a region, I think you select nodes. So let's grab on element. We'll grab a little section here. Let's see where we're at there. So we're just going to take this little section here, and we don't want to split all the way through the model. We're just going to split through this section. Okay, and we're going to split this way, not through the thickness, but through this. And you can see it split, and then it gets to the end of my selection here and gives me a little triangular element. So it's pretty crafty. It seems like a simple tool, but it's pretty powerful, and I think it'll handle a lot of stuff. All right.
One of the other questions was about the new geometry from Mesh, and we did not cover that this session. I believe we'll cover that in one of the next webinars that we do.
And I believe that the Siemens has some demonstration videos of their new resources for V11, and I'll go ahead. Let me see if I can. I don't have my email loaded, but there'll be a link. I'll include it with this webinar upload package. There'll be a link to their videos because they've created short little videos on a lot of these new features. Some of the ones I didn't cover, like geometry from Mesh and solid bolt preload. They have great videos for those things online. All right. Anyways, at this point, we're getting close to the hour, so I want to wrap things up. Thank you all for tuning in. I'll try and get all of this information organized and uploaded to the website maybe next week. Again, the username and password will be in the signature block, so if you look to the email from me that had the invitation to this webinar, scroll down to the signature block. It's Femap and Nastran. If you guys don't want to look, see if we... Go to resources, restricted. Oh, well, it remembered it, but Femap NX Nastran is our password. And I think that about covers it. Nate, you got anything else?
No, I don't believe so. Any of the other questions, we'll go through them, like Adrian said, and if there's anything we didn't answer, we'll make sure to answer those in the email that goes out. The only other question on there is, when is Femap 11 available? And I answered that with text, but it's available now. You can download it from the Siemens website, ftp.ugs.com. You'll need a WebKey account to get past their security to get in to download that. And if you don't have a WebKey account, give us a call. We can help you get one set up.
Excellent. Thanks, Nate. Thanks, everybody, and have a nice day.